Okay, so there's two operators, two differential operators that we're going to talk about. One is the divergence, one is the curl, and we're going to start with the divergence operator. Now let me just come back up here to the warm-up and make a little addition. One way we can sort of write the gradient operator in this way. Partial x, partial y, partial z. These are new symbols. This just means the partial derivative with respect to x. So this partial sub x is the derivative with respect to x operator. The partial sub y is the derivative with respect to y operator, and the partial sub z is the derivative with respect to z operator. Okay, it just means put in a function and take the derivative with respect to whatever the variable in the subscript is. So we could write this as gradient operator times f, or gradient operator of f. Remember, gradient is operator, so it takes in a function and spits out a function. This is just going to be the partial derivative of f with respect to x, the partial derivative of f with respect to y, and the partial derivative of f with respect to z. This is exactly the gradient that we've seen before. This just means the x derivative. The second component just means the y derivative, and the third component just means the z derivative. Okay, so let's come down here now to answer this question. So the divergence operator is a differential operator that acts on vector fields. If f equals f1, f2, f3 is a vector field, then the divergence of f, that's what the div is, the divergence of f is equal to the del operator, or the gradient operator dotted with f. So in other words, it's something like this. So this is a new type of dot product. So it's not technically the official dot product, but it is good notation. And so good notation beats mathematical correctness, basically. Okay, so what is this? Well, just do what the dot product says. It's this times this. So this is partial x times f1 plus partial y times f2 plus partial z times f3. Only now, instead of this being normal multiplication, it's an operator. So this is just the x derivative of f1, the second is the y derivative of f2, and the third is the z derivative of f3. We will talk about the physical, or one physical interpretation of this in a moment. For now, let's just do an example. So we want to find the divergence of this vector field. So it's going to be a scalar, and so it's just going to be the x derivative of the first component plus the y derivative of the second component plus the z derivative of the third component. So the divergence of f, or gradient dotted with f, is equal to the following. So I'm going to kind of color code this. So we'll do the x component first. So the x derivative of the first component is 2xy plus, the next one I'll use red. It's going to be the y derivative of the second component. So this is plus 2y plus the z derivative of the third component. So this is going to be 3z squared minus x squared. So this is the divergence of the vector field that I just did. Okay, now to answer this question about the physical interpretation of divergence, I'm going to open up Dr. Yaskin's book, and I suggest maybe you somehow do the same and try to listen to this in the background or something. Okay, so let's look at this example. So this is sort of a one-dimensional example. So let's suppose we have a velocity field that just has one component. Its derivative is just the x derivative of that component. So this is just sort of, so the idea is that f is a vector field, and it is a velocity vector field, and it's just in one dimension. Okay, so it represents the velocity of water flowing, or the velocity of some fluid flowing in one dimension, say like inside a hose or something. Okay, its divergence is just going to be the derivative of, because that's, remember, the divergence is just the sum of the different derivatives. So if there's just one component, the divergence is just going to be the derivative of v with respect to x. That's what this is here. Okay, now let's see what happens if the derivative is positive. Okay, if the derivative is positive, then v1, so if the divergence is positive, then it means this derivative is positive, and it means that v1 is getting bigger as you move to the right. Okay, so let's look at this green ball here. So both of these represent the vector field. So this blue arrow here and that red arrow, those are both the vector field evaluated at the edge of the circle. Well, observe what's happening here. Since this blue arrow is bigger than the red arrow, then there is more water flowing into this green circle than there is flowing out. And if you get an even smaller and smaller circle, the difference stays the same. Okay, or not stays the same, but relatively it stays the same. If you're over here, there's more water flowing out, or there's more liquid flowing out than there is flowing in. Okay, so uh, So for this example, at least, at every point, the divergence is positive, meaning that if you look at a really small ball around a point, there's more water flowing into that region than flowing out of that region. Or really, I shouldn't say water, I should say there's more fluid flowing into that region than out of that region. And if you're trying to wrap your mind around how that can happen physically, considering things like conservation of matter, we'll talk about that in a moment. Okay, and similarly, if the divergence is negative, then the opposite happens. So I guess I shouldn't say similarly, I should say oppositely. If the divergence is negative, the opposite things happens. So now there's more water. If the hose is going this way, there's more water flowing into the interval than flowing out of the interval. Okay, now if we come down here, so at least in one dimension, what we've sort of observed, the divergence tells us is if the divergence at a point is positive, then it means that for a small ball around that point, or a small interval around that point, there's more fluid flowing into that interval than there is flowing out. Or sorry, I'm sorry, I said that backwards. Um, if the divergence at a point is positive, it means there's more fluid flowing out of the interval than there is flowing in. And it's opposite if the divergence is negative. If the divergence is negative at a point, then if you look at some small interval around that point, there's more water flowing in than there is flowing out. Okay, so let's look in two dimensions. So again, something similar is going to be true here, and I'll let you look at the details. But if the divergence, if both terms of the divergence are positive, then the divergence overall is positive, and we have something similar going on. Okay, if I move this around, there are parts, if you look up here, sorry, I needed to move it to a better spot. Okay, so if you look at the divergence here, notice what's going on. So these, again, these arrows represent some sort of velocity field. And notice that there are some small arrows representing fluid flowing into this ball. Okay, but the blue arrows represent fluid flowing out of the balls. And so just kind of eyeballing it, it looks like there's more fluid flowing out of this region than there is flowing into the region, and that's consistent with the fact that it is a positive divergence. And if we come now over here and look at something like this, okay, well, this is a negative divergence, and if I look at this point, the divergence here is negative, and observe that again, there's some small blue arrows that represents fluid flowing out, but there's big arrows that represent fluid flowing in. So there's more fluid flowing into this region than flowing out. Okay, so this is what happens if the two terms of the divergence are both positive, and this right here, the second example we looked at, is what happens if the both two terms in the divergence are negative. Now, if the two terms have opposite signs, but the sum is positive, then there's sort of like, kind of an average thing going on here, that on average, there's more fluid flowing in than flowing out, or more fluid flowing out than flowing in. And if it's negative, the divergence is negative, and the two terms have opposite signs, then something similar is true. There's more fluid flowing in than flowing out. So this is the physical interpretation of divergence. Let me write that in the sheet. Okay, so the physical interpretation is that if if the divergence of a vector field at some point x naught, y naught, z naught is positive, then there is more fluid flowing away from the point than there is flowing into the point. Okay, and sort of the opposite thing is true if the divergence is negative. If the divergence is negative, there's more fluid flowing into the point than there is flowing away from the point. Okay, so positive divergence means there's fluid that's kind of going away from the point. Negative divergence means there's fluid going into the point. Okay, so water is incompressible. Use the divergence operator to denote this. Well, what this means essentially is that the amount of water is conserved, or the volume of water is conserved. So what this means is that the divergence is 0 at every point, because if you look at any point, the same amount, the amount of water that's flowing into that point has to be equal to the amount of water flowing out of the point. And one way that we can write this is to say that the vector field is divergence free, or we could say div of the vector field is equal to 0. Here I'm using v because we're thinking about the vector field as being a velocity field. And this is also true in electromagnetics. And so I just realized that I wrote the wrong answer here. This is the answer that I wrote here should be the answer here, but it's basically the same here. So sorry about that. Okay, now let's answer this question. Water is incompressible, which means that divergence is equal to 0. That's one thing that it means. But why would some models of water flow not satisfy this property? In other words, why would some mathematical models of water flow not satisfy this property? In other words, not be divergence free? Well, the reason is the following. Maybe if the divergence of a point, if the divergence at a point x naught, y naught, z naught is less than 0, this is a sink. We call this a sink all the time. And it could represent a drain, for example. So maybe you want to have some mathematical model that models the way that the way that water flows in a sink. The divergence is going to be negative at the drain because the water is sinking down into the drain. That's why it's called a sink. Okay, even though the water that you're modeling is incompressible and satisfies all of the conservation laws that you think it should satisfy, it's kind of going out of the sink, so it's going out of the modeling area. And so in that way, we might want to model fluid flows that is divergence free. And similarly, if the gradient is positive, or if the divergence is positive at a point, it could mean that there's water flowing in at that point. So for example, maybe you're modeling water in a sink. If the divergence is positive at a point, we say that point is a source. So it could be modeling, for example, turning on the faucet. And now the divergence is positive because at that point there's water flowing into it, but there's more water flowing into it than there is, or there's water flowing out from that point because the faucet is on. So the divergence is positive. Okay, in the next videos, we'll look at curl, and we are going to look at some more examples as well.